All right, let's go ahead and take care of this homework. So write out the balanced chemical equation for the decomposition of ammonium nitrate into nitrogen, oxygen, and hydrogen gases. Alrighty, so I've got NH4NO3 state. What state is this in?
Solid.
It's a solid. Those are your only two options because this is an ionic compound, but it's not wet. It's a solid. And it's going to decompose into N2 gas and O2 gas and H2 gas. And balancing it, I need a 2 right here and a 3 right here and a 2 right there and a 4 right there. Is that good? 1, 2, 3, 4, 1, 2, 3, 4, 8, 8, 6, 6. Yeah, okay. Alrighty. Cool, I gave you no room. Awesome. Sorry about that. Let me make some room here. Okay. So back to this. So if I started off with 25 grams of the ammonium nitrate, how much of the hydrogen gas could I make? Okay. So I've got 25 grams of NH4NO3. Then I'm going to put 1 mole NH4NO3 and grams NH4NO3, and I can put moles NH4NO3 and moles H2 and moles H2 and grams H2. So before you do any calculations whatsoever, you can write all of this stuff out. This is what every single one of these problems are going to look like. You start with the thing you start with, you go to the thing you're looking for, and you start off with the mass that you were given for the first thing. So it's always going to be 1 mole of whatever it is turning into grams. And so the mass for that ammonium nitrate, a mole of that is 80.0434. And the numbers that we're using for the mole to mole conversion, it's going to be a 4 for the hydrogen, and it's going to be a 2 for the ammonium nitrate because that's what the balanced chemical equation says. And then the mass for an H2 is 2.0159. And that's it. Somebody have a mass for us? Grams of H2? Yay, nay?
1.3. You just around it to 2.6.
Yeah, that sounds good. 1.3. So 1.3, and that's the that's the mass of hydrogen that's going to be created from this. Okay. What is this reaction? It's a decomposition reaction, but we talked about this a little bit. What is this? It's a bomb. It's an explosion, right? It's a solid that got turned into gases. So you want to blow something up, you'd use ammonium nitrate and a bunch of heat to get it going. Okay, so we are gonna, how many grams? What's the name of that substance? The M207? Mn207? Manganese.
Something oxide.
I'm sorry, what did you say, Amanda?
I can't remember what 7 is.
You can't, there's no, it's sept. No. Sept is what 7 is, but that's not.
Word for that.
What kind of compound is this? Do you know what a pinata is? Everybody know what a pinata is? That's what you're gonna feel like on the exam. Because that's what the question you're gonna see on the exam is gonna look like. But it's gonna be worse because I'm not gonna give you the formula. You're gonna have to figure out what manganese 7 oxide is, which is the name of that substance.
It is just manganese 7 oxide.
Yeah.
Oh.
What kind of compound is it? It's ionic. It's got a metal in it. It's ionic. So can you use sept for 7? No, because that's only for covalent compounds. What kind of metal is it? It's a transition metal with a variable oxidation state. So you are required to tell me what the oxidation state is. So it's 7 because there's 2 of them and there's 7 oxygens. The only way it works out is I get plus 14 from the 2 manganese because I've got minus 14 from the 7 oxygens. So manganese 7 oxide. Okay. So manganese 7 oxide, how much of that stuff can be formed if I've got 196 grams of, what's the next thing?
Potassium.
No.
Potassium permanganate.
Say it.
Potassium permanganate.
Yeah, okay, so first day of class, I told you needed to know those polyatomic ions, right? So that MnO4, that's one of those polyatomic ions that you're supposed to already know. That's potassium permanganate. Okay. So if we start off with 196 grams of potassium permanganate, how much of the manganese 7 oxide can you make? What is this question assuming?
Have an unlimited amount of
Come on.
sulfuric acid.
Good job. So this is saying I've got 196 grams of the potassium permanganate, and it's all going to be used up because I have plenty of sulfuric acid. Alrighty. So I'm going to start off with 196 grams of KMNO4. And then it's 158.034 grams of potassium permanganate for 1 mole of potassium permanganate. And then, oh, well, we forgot to do something, which was what? We didn't balance this equation out, but
It's just a 2.
it's just a 2 right there. Really? 4. Okay, so there's 2 potassiums, and there's 2 manganese, and there's 2 hydrogens, and there's 1 sulfur, and there's 8 and 12 oxygens, and there's 7, 8, and yeah, sweet. Well, that was easy. So I need a 2 mole of KMnO4, and then I'm looking for manganese 7 oxide, so that'll be a 1 mole of Mn2O7, and then for every 1 mole of Mn2O7, it's 221.872 grams Mn2O7. 7. Okay. So I got 196 divided by 158.043 divided by 2 times 221.872. Got 137, how many sig figs? A boatload. 0.587 grams manganese 7 oxide. So we need all 6 of those significant figures because we started with 6. Everybody okay with me saying we had 6 to start with? Okay. So whoever did this was really good with the balance, right? And their balance went to 3 decimal places. Okay. How many grams of potassium, or sorry, what's that first thing in B?
Potassium sulfate.
Potassium sulfate can be formed from the potassium permanganate. So this time, basically it's the same sort of question, it's just we're looking for a different one of the reactants. So I'll go 390 grams of KMNO4. And then for every 1 mole, KMNO4, I got 158.034 grams KMNO4. And for every 2 mole of the KMNO4, I've got 1 mole of potassium sulfate. And for every 1 mole of potassium sulfate, I've got 174.26 grams of potassium sulfate. So 390 divided by 158.034 divided by 2 times 174.26, and that's 215, 215.013 grams of potassium sulfate. What did this, what assumption did B make?
Yeah, we already knew
So we had an infinite supply of the other stuff.
Same assumption that it made for A, right? That we had plenty of potassium, or of sulfuric acid. Okay. So, what are we doing with this one? We're going to react 375 grams of zinc metal and 225 grams of fluorine gas, and we want to know what's going to be left in the container. All right, so let's do this. Let's give ourselves some more room. There. And I'll put the pen. All right, so what's the reaction look like?
CN plus F2 and ZN F2.
That's easy. States? Zinc's a solid,
Yeah, gas.
fluorine's a gas. Why is it a solid?
There's no water.
And? What kind of compound is it? It's ionic, so it's either it's either solid or it's aqueous. There's no water present. Plus, do you have a zinc rule? No. Do you have a fluorine rule? Nope. You don't have a rule for either one of them, so I would not ask you to figure out what the state of this is going to be. It is aqueous if it was wet, but you wouldn't be able to figure that out. Okay, nicely it's balanced itself. So remember what we're doing here. We're initially trying to figure out which of these two reactants is the limiting reagent, correct? So I need to figure out if the zinc is going to run out first or if the fluorine gas is going to run out first. So I do a railroad track with the assumption that I have plenty of fluorine, and then I do another railroad track with the assumption that I have plenty of zinc, and then I figure out which one of those numbers is smaller, and that'll tell me which is my limiting reagent. So I'll go ahead and start off with the zinc. And so it's 65, sorry, no, my bad. It's 375 grams of zinc. That looked terrible. Erase. And then for every 1 mole of zinc, it's 65.39 grams of zinc. And for every 1 mole of zinc, I have 1 mole. And what's the name of this thing here? Well, zinc's a transition metal, so don't I say zinc 2? Is that right? It's the only oxidation state it has, so we don't say zinc 2. Remember, zinc, cadmium, and silver were the 3 transition metals that had one oxidation state, even though they're transition metals, so we don't say what the oxidation state is. So this is just zinc fluoride. And the zinc fluoride's Dang, I don't have it written down. It's 39.9681 plus 65.39. So it's 105.358. And so then that's multiplied by 375 and divided by 65.39. And I get 604, yep, grams of zinc fluoride. Okay, so let's figure out from the fluorine. So I've got 225 grams of fluorine gas. And for every 1 mole of fluorine gas, I've got 37.9681 grams of fluorine gas. For every 1 mole of fluorine gas, I have 1 mole zinc fluoride. For every 1 mole zinc fluoride, I have 105.358 grams of zinc fluoride. Bless you. And so that's 225 divided by 37.968 times 105.358. And I got 624.356 grams of zinc fluoride. Excellent. What do I know?
Zinc is your limiting agent.
That zinc's my limiting reagent. Okay. So I know zinc's my limiting reagent. I know that the zinc is going to be running out first. I know the moment that I've made 604 grams of zinc fluoride, what happens?
You have 0 zinc left.
I have 0 zinc left, so the reaction just stops. So that means I must have some leftover fluorine in the container. So the answer to this question is going to be I've got 0 grams of zinc. I've got 604 grams of zinc fluoride, and since this is a very simple problem as far as the number of reactants and products, I could easily figure out how much of the fluorine is left by doing what? Okay, so I started with 375 and 225 grams of reactants, and so I've got 600 grams going in. I need, what, 700. Like, that can't be right. I've got 700 grams of stuff going in. That's my reactants. And in the end, I have 604 grams of my product, zinc fluoride, which,
I'm still getting 600.
Yeah, 600.
oh, 600. Oh yeah, that is 600. Okay, so what did we do wrong up here? Did I not add up my zinc fluoride correctly? 65.39 plus 18.998403 times 2. That's 103, not 105. So this is, oops, 103.387. 103.387. All right, so times 375 divided by 65.39 equals 592.905 grams of zinc fluoride, and this one will be times 225 divided by 37.961. So 612 grams of zinc fluoride. So this is 593 And so then that means I've got 7 grams of fluorine gas left over. So in my container, I've got 0 grams of zinc, 593 grams of zinc fluoride, and 7 grams of leftover fluorine. Okay. And last question for this one.
The combination.
So this one's a combination reaction. This one is a redox reaction. And this one is a decomposition reaction. So decomposition, redox, and combination reaction for those 3.